Welcome, ladies and gentlemen. This is the first of our 2 videos on titrations, on what happens when you have a weak acid or a weak base involved in your titration. In this video, and there are going to be 2 videos on titrations, I am going to be talking about the first 3 of these points. So with weak acid, strong base titrations, what is in the flask at different points in the titration, and especially things that would influence pH. How is the titration curve altered when you have a weak acid, and introducing something called half equivalence point. And the other 3 points, sample calculations, indicators, and polyprotic acids, I'll be talking about in the second titration video. So weak acid, strong base titration, or strong acid, weak base titration is the last of our secondary topics in equilibrium. And it comes in this order for a reason, because it is going to continue to build off of what we've been talking about in terms of buffers and common ion problems. And yes, we are absolutely still using all of our primary topic skills. You will still be writing equilibrium expressions, filling out ice charts, and solving for the unknowns. So what is in the flask, the first portion of this? When you have a titration, realistically, you have 4 distinct sort of areas that you can consider in your titration. You can sort of work out, hey, initially, what's going on? So we're going to be talking about initially what's in your flask, and then you can say before the equivalence point. So, you know, the equivalence point, again, middle of that steep section right there. If you're before that in your titration, then you have a discussion about what's going on in the flask. And there's sort of a 5th point that goes along with that, something called the half equivalence point, which we're going to be talking about. And then at the equivalence point, we're going to be talking about what's in the flask at the equivalence point there, and then after the equivalence point. So we'll be paying attention to those sort of 4 broad definitions of our titration, sort of breaking down our titration into those different regions. So first up, what is in the flask? Initially, so in this example, we're going to be talking about a weak acid, strong base titration. So if you can imagine like HA and NaOH, a weak acid and a strong base. Initially in your flask, before you started your titration, what do you have present? And you have present just the weak acid, so just your HA. And it's weak acid, so it hasn't really dissociated much at all. And so we mostly have the HA form of it. You know, it's not a H plus and it's not A minus, and you don't have any common ions. So what is it that controls the pH? Well, the HA is going to be what controls the pH initially. How do you do that calculation? Well, this actually goes way, way back at this point to our 3rd primary topic of equilibrium, calculating concentration from K. So this is just, you know, write the reaction, HA, fill out an ice chart, write the expression, and solve for H plus that way, and then you can get pH from that. So that's how you calculate it. That's essentially describing the calculations. And we've done those calculations before, so this is sort of reminding you that yes, you can do that type of problem already. In fact, I'm not even going to do an example of it, because if you just look back, you've already done that. So before the equivalence point, so let's move on. Let's start our titration. So we have our weak acid in our flask, and then we start adding some sodium hydroxide, but we have not yet reached the equivalence point. So what if we are before the equivalence point in our titration? Then what do we have in our flask? Oh, this is a big one. So before the equivalence point is when moles, in this case moles of our weak acid, will equal moles of our sodium hydroxide, right? We know that, and that's the equivalence point right there. When moles of H plus equal, when moles of acid equal moles of base. If we're before that point, then some, but not all, key critical point, of our HA has been neutralized. Some but not all of our HA has been neutralized. So the OH minus, this is our limiting reactant, right? It's getting completely used up. So we're not going to have any hydroxide in our flask at that point, because it's going to be the limiting reactant. It's going to go completely away. And we've used up some of our HA through this reaction. This is a neutralization reaction. Right, this is neutralization. What this reaction has done, and this is a huge critical point here, is that we've actually generated some A minus. So we've made this, which means we have it in the flask, but we still have this. right? So you've used up some of your HA, but not all of it, and by using up your HA, you've generated some A minus. So what do you have in the flask? Hey, you have HA and A minus. Hey, you have HA and A minus. Hey, you have a weak acid and its conjugate base. We got ourselves a buffer situation. So if you are before the equivalence point in a weak acid strong base titration, and you're somewhere, in this region here, or you're not yet at the equivalence point, but you've certainly started your titration, then you have a buffer. You have HA and you have A minus together. And how do you calculate the pH of a buffer? Henderson-Hasselbalch equation, right? We have a formula for that that allows us to do that easily. So in this calculation for pH before the equivalence point, there are really two components to it. You can't just jump straight into your Henderson-Hasselbalch equation. What you have to do first is a stoichiometric calculation. And basically what this is describing is, notice this is the neutralization reaction. You want to use a BCA chart. Ooh, we haven't talked about that for a little while. That uses moles, not molarity, to work out how many moles of HA have you used up and how many moles of A minus have you generated, and then recalculate concentration of both the HA and your A minus. So this is basically the BCA chart in here. Recalculate concentration, and then in order to calculate pH, you have to do an equilibrium calculation. That's the Henderson-Hasselbalch formula. Once you've recalculated your concentrations, then you just use that. So if you're in a titration involving a weak species, weak acid or weak base, with something that's strong, and you're before the equivalence point, it's really a two-step problem. Number one, do a BCA chart to work out moles, then recalculate molarity, then use the Henderson-Hasselbalch equation to get pH, because you have both weak acid and the conjugate base in the flask at the same time, so you do have a buffer. Now, a very special point that's before the equivalence point is something called the half equivalence point. Now, the equivalence point, as we've been saying, is when moles of acid are equal to moles of base. So this is our equivalence point right here, right in the middle of the steep section. We've seen that again and again and again. Well, the half equivalence point is based on the titration curve. So at the equivalence point, and that's 10 milliliters. For the equivalence point. Half equivalence point is when half of the moles of base have been added, or acid. This one is base. So when half of the moles of base have been added, that's going to be half the volume. So 1/2 of 10 milliliters is 5 milliliters, right? So I go to this particular point, 5 milliliters, and that is what is called the half equivalence point. And I go up right there, half equivalence points. So see how I worked that out? The equivalence point was at 10 milliliters, so I cut it in half and got to 5, and I saw that that was the half equivalence point. Now, that's an incredibly, incredibly special point, which we're going to talk about sort of on the next slide, because it allows you to simplify some of your calculations. So basically, we're halfway volume-wise to the equivalence point in terms of how much base we've added. Now, if we are halfway there, then we can consider with the Henderson-Hasselbalch equation, because half the moles of the base have been added, then half the moles of our weak acid has been turned into its conjugate base, right? If you're halfway to getting rid of all of your weak acid, that means that you still have half of your weak acid left, but half of it has been turned into its conjugate base. So that means that we are at this situation right here. We pull back from buffers, right? This reminder that if you have an equal amount of the weak acid and its conjugate base present, then right, in our Henderson-Hasselbalch, if these two are equal, then you're taking the log of 1, which is 0, and you have that situation where pH is equal to pKa. The huge thing that I want you to know about this half equivalence point is that we have equal quantities of both HA and A minus. You have neutralized half of your HA, so you have generated the exact same amount of A minus. So that means you have the same amount of each one. That means that if they're equal, then pH is equal to pKa. And that the pH is equal to pKa, and if the problem is asking you for pH and it gives you a Ka value, oh my gosh, just recognize that you're at the half equivalence point and take the negative log of the Ka value, save yourself some time, and then that's how you're going to get pH. just putting this up again because, yes, it is truly that important. At the equivalence point, so I'm sorry, this is at the equivalence point. We moved on past the half equivalence point, and now we're considering a different situation. If we're at the equivalence point in a titration, then what do we have in the flask? Well, at the equivalence point, all of the weak acid has been reacted, neutralized with the base, right? Because moles of acid are equal to moles of base. But you don't have any excess of your strong base. You truly have literally stoichiometrically equivalent amounts. All of your weak acid is gone. All of your strong base is gone. So this neutralization reaction that's shown right here, you do not have any HA, you do not have any hydroxide. They are both totally gone. They're used up. You don't have them anymore. They have completely consumed one another, right? Moles acid are equal to moles base. But what do you have in your flask? Well, you have this in your flask, right? You have water and you have A minus. A minus is significant because it is the conjugate base of the weak acid. So therefore it is a weak base. Now granted, it's not a strong base, but it is a weak base, meaning it does have an impact on pH. So this thing right here affects pH. You don't have any HA, you don't have any OH minus, but you do have A minus, and A minus will change the pH of the solution. So therefore, at the equivalence point, what controls pH? A minus does. A minus has a big impact on pH. And what this is trying to say is this enormous point that's down here, this absolutely huge point. Why we do not define equivalence point in terms of pH. And you can't just say, well, when it's the pH of 7, that's not, no, that's not the equivalence point. No, that's not true. Because you can have equal amounts of HA and OH minus and not have a pH of 7. If you've generated a weak base in having equal amounts of HA and A minus, you're going to have a pH greater than 7 at the equivalence point. This is such an enormous point. Put like all the star circles next to this in your notes. That's huge. It's absolutely huge for this weak acid strong base titration. Looking at the graphs, showing how this is represented graphically with our titration curves, if you have a weak acid and a strong base, at our equivalence point, which is right here, so all the weak acid is gone, all the strong base is gone, but we do have A minus present, and this is a weak base. Notice that our pH is 9, so we have a higher pH at our equivalence point. And then looking at the flip side of this, so this is a weak base plus a strong acid. So we've started with the weak base in the flask, and when we've added in our strong acid. So now the situation is flipped, because now at the equivalence point, all the weak base is gone, all the strong acid is gone, but now what we've generated is HB plus the conjugate acid of the weak base. And it is, in fact, a weak acid, right? Weak bases have weak conjugate acids. So the only thing in the flask there is something that's actually acidic. And notice that the pH is somewhere between 5 and 6. So we have this acidic pH at the equivalence point. And that's how you can actually tell what type of things you were involved in your titrations simply by looking at the titration curve and looking to see where does that equivalence point fall. If the pH is 7 on the dot, then you knew that you were titrating a strong acid and strong base. If the pH is above 7 at the equivalence point, then you knew that you had a weak acid and a strong base. You had to have a weak acid to generate that basic pH at the equivalence point, to generate that conjugate base. If the pH is less than 7 at the equivalence point, then you know you had to have a weak base with a strong acid. The weak base would generate its conjugate, which is a weak acid, getting us that acidic pH at the equivalence point. What's in the flask? Continuing on. So how to basically do this calculation for pH at the equivalence point. Calculating pH is an equilibrium problem. So you can't use Henderson-Hasselbalch because you don't have both HA and A minus. You only have A minus. There's no more HA. The HA is totally gone. Very typically Very typically, if it does ask you this, you're going to have to convert Ka to Kb, because usually they'll give you Ka, but again, at the equivalence point, all the Ha is gone and all you have is A minus, so you're writing a different reaction. You want to write a base dissociation reaction because the only thing you have is a base. You can't write an acid dissociation reaction because all your acid is gone. So you'll typically, very typically, have to convert Ka to Kb, and then it's using our standard equilibrium problem mindset, meaning you're going to write a reaction, we're going to fill in an ice chart, and we're going to go to the expression. You cannot use Henderson-Hasselbalch here, and you do have to start by working out your concentration of A minus. After the equivalence point. So what if we move past the equivalence point? Well, things actually get a little simpler here. So all of our HA is gone because that was gone at the equivalence point, but now we have excess strong base. I'm going to say just hydroxide. So what you have in the flask is both A minus and OH minus. So you have two bases. You have a weak base and you have a strong base. Well, okay, how strong is the strong base? Really, really, really strong. So what is it that's controlling the pH? Basically, how do you do a pH calculation here? Well, you're going to do the pH calculation through the amount of hydroxide that you have left over. Meaning, yes, there is A minus in the flask. However, it is so much weaker than hydroxide that it will not have a measurable impact on pH compared to the impact that the hydroxide will have. So it's basically saying that, yeah, the A minus is technically doing something to the pH, but it's on the order, it's so much less than what the hydroxide is doing to the pH that we're going to essentially ignore it, and we're just going to calculate pH based on excess hydroxide. And this is actually not an equilibrium calculation. So this is straight up the calculations you were doing in your acid-base unit. You know, how many moles of excess hydroxide do you have left over, recalculate molarity, and then get POH, and then get pH from that. So we are pulling in the BCA chart. So it's actually not an equilibrium calculation anymore, because the thing that's controlling the pH at this point is something that is not an equilibrium thing, really. It's just that hydroxide sort of doing its hydroxide thing. So just sort of summing up what we've talked about, what's in the flask at the different points in this weak titration. Initially, right, the only thing that you have in your flask, this is just HA here. That's all you have initially. And then you start your titration, so you start adding stuff in. So like in here, right, this is where you have the buffer. Right, because this is when some of your HA has been neutralized and turned into A minus, but not all of it, right? So you have both HA and A minus before the equivalence point, but after the initial. Equivalence point, middle of the steep section here. And if we read our curve, then that's 25 milliliters for the equivalence point. So if I take half of that, I get to about 12.5 milliliters. And that is the half equivalence point. So right here, that's where you have HA being equal to A minus, right? You are literally halfway to your equivalence point, so half of your moles of HA have been consumed to create A minus, which means that you have equal quantities of both of them, and it's at that point when pH is equal to pKa. And then if we're at our equivalence point, what do we have in our flask? You don't have any HA, you don't have any hydroxide, you just have A minus, which is a weak base. So you will notice the basic pH at the equivalence point here. And then after the equivalence point, now we just have excess hydroxide that controls pH. Yes, there's A minus in the flask too, but it's too weak to do anything in terms of calculating pH. So it's like, what do we have in the flask? Initially just HA. Before the equivalence point, we have both HA and A minus, so we do indeed have a buffer. At the equivalence point, we just have the conjugate base. And then after the equivalence point, we just have excess hydroxide. And yes, some A minus as well.